So in section 5.1, we're going to talk about approximating areas. So when we look at approximating areas, this is something that has been around for millennia. And it was not just known in the Western world. It was known in China. It was known in South America. It was known in Africa thousands of years ago. So this is something that's been known all over the Western world, as well as the Eastern world and in parts of South America in the ancient Mayan and Aztec and Incan civilizations. So this kind of idea is not new. Basically, it's called finding the area by exhaustion. Archimedes is the one who did it in the Western world in Greece. So Archimedes looked at a process. It's been called the method of exhaustion, where you basically take some shape. In their case, they were taking a circle because they needed the area of a circle. And you can imagine that at least in the Western world, this was a very difficult problem because we know the area of a circle is pi r squared, right? So the area of the circle depends on an irrational number, pi. Well, remember the Pythagorean theorem and how they drowned the first person who realized that there were numbers that were not the ratio of two integers? Yeah, this was a very threatening idea. They didn't really understand what irrational numbers were at this time, and they didn't know how to calculate with them or how to approximate them. But they came up with a method of exhaustion, and again, it was known in other places as well. So don't think that all mathematics is only ever taken in the Western civilization. That is not the case. So when we're looking at this, all societies, and I think actually it may have originally come out of China and Northern Africa, were two of the first places where we know for sure they were using this method. And then this method got taken from Northern Africa and shared with Greece. So there was a lot of travel back and forth between Northern Africa and Greece in the early days, and a lot of the mathematics went back and forth. So at any rate, the method of exhaustion takes the circle and divides it into known shapes, shapes for which the area could be computed. So you'll see here in blue, this is basically a square. So they started with the square, and then they divided the sides of the square with the red triangles. Now they could take the red triangles, and let me put a side on the red, and then they could do this on the red triangles. They could make a bar coming down like this, which basically turned these red triangles into right triangles. And then they could do 1/2 the base times the height on the right triangles. Or at the time of Archimedes, it was realized they had sort of started to come up with the Pythagorean theorem, so they were able to use the area of the triangle. They had an approximation for the area of a triangle. And then that still left some space that was undone. And you see these green triangles out here. So they divided that up again. And so they divided it again and again and again. And the more they divided it into these triangles, the closer the approximation was. This is a well-known method throughout the world in mathematics history. Now, what we want to do is we want to do something similar to what they did there. We want to approximate the area under a curve, however, so over some closed interval. So what we're going to be doing is we're instead going to be looking at some closed interval between A and B, and we have some function like this, and we want to take the function and we want to divide this region between A and B, and using the x-axis as the bottom and using the curve of the function as the top, we want to see if we can figure out how much area is in this shaded region right here. And we're going to use a method of exhaustion pretty much just the way that Archimedes did and the ancient Chinese and the ancient African mathematicians did as well. All right. So we're going to be using a method of exhaustion called the Reimann sum. Now, we're not going to be using triangles as Archimedes did in finding the area of the circle. We're instead going to use rectangles. Now, that is not the only method. There are actually other methods. There's one called the trapezoidal rule, where you use trapezoid shapes, and I'll show it to you today. And then there's another one called Simpson's rule, where you actually use 3 sides of a rectangle, but the top of the rectangle, instead of being a flat side, is actually part of a parabola. So that's called Simpson's rule. So there are various ways of creating shapes to approximate the area. Now, we're going to use rectangles exclusively in this class, but in Calculus 2, if you go on to Calculus 2, you'll study the trapezoid rule and Simpson's rule, at least in my class. We do it with a Python program. So when we're looking at this, we're going to approximate the area under the curve using rectangles. So what we're going to do is we're going to divide the region into sections like this, and we're going to divide the top at one particular point or another. And we may get an overestimation or we may get an underestimation of the area under the curve, but the more rectangles we take, the closer the approximation will be. This is the basic idea behind a Riemann sum. So let's go ahead now and take a look at some examples that are better drawn than mine. So this is what's called a left Riemann sum. So when we're looking at this one, this is a left Riemann sum. And it's named for Bernard Riemann, who was the first person to come up with these sums. Sometime, gosh, I really don't know. It would have been in the 1800s. I want to say it was in the 1800s. Came up with this method of approximation. So the left Riemann sum, why is it called left? Well, if you look at each of the boxes, they're using the left endpoint of where it intersects the axis, the left endpoint of the box, to be the height of the box. Does everybody see that? It's that left endpoint that sets the height of the box. And they're dividing the x-axis up into what's called a partition. So this is a partition that we see right here. All right. Now, what is the partition? Well, A is equal to x naught, which is the first value in our partition. And B goes up to x of 8 because there are 8 partitions. In general, we would say that B is equal to x sub n, where n equals the number of partitions. Now, the more you take, the better the approximation, but the more calculation you have to do. So we're going to learn some techniques to help us simplify some of the adding that we're going to have to do, because you're going to have to add the area of all these rectangles, and that can get a little tedious. 8's great, but 100 would be fantastic. And so adding together 100 is pretty tedious. And so we're going to come up with formulas that will let us do it more simply. So then they're divided up into x1, x2, x3, x4, x5, etc. And a left Riemann sum uses the left endpoint of the interval as the height of the box. If you're looking at this next picture down here, this is also a left Riemann sum. It is a little bit more difficult to see because it's hard to see where the height is coming from, but you can see it more clearly on this first and second partition over here. So again, this is x naught at this far point right here. And then we have x1, x2, x3. I can't write that small, right? They're pretty small, going all the way across to x sub 32. Notice how much better these 32 rectangles fit the same curve as compared with 8 rectangles. In the 8 rectangles, you can tell that we are underestimating the area, because we've got some space right here that isn't shaded, but is under the curve, right? So we're leaving this white space out. So this space that you see right here, we're leaving that space out, and we're leaving that space out, and there's a little bit right there. Can't see any there, tiny bit here, a little bit here, more here. So we're leaving out some, so we're underestimating the area. The more rectangles, the smaller the area that gets left out or over included, and so the better the approximation. Now we want to talk about what's called sigma notation. Sigma notation is what we use to simplify taking the sum of the area of all of these rectangles. So again, we're talking about multiple rectangles, 100 rectangles, 200 rectangles. You really don't want to compute those by hand and have to add together 100 or 200 values. That would just be that. I mean, what are the chances any of us could do that without making a careless mistake? Not good. So we call this sigma notation or summation notation. And the symbol that we use looks like this. Now, technically, it should have, I'll try to draw it better. It should be parallel at the top and the bottom, but this is my lazy way of writing it. And this is the accurate way of writing it. All right. And it is, in fact, a summation. Now, you may be wondering how this relates to what we were talking about in the antiderivative section. It doesn't relate directly to antiderivatives, but it does relate to what are called definite integrals. So not the indefinite integral, but an integral of a different type, where the definite integral measures the area under the curve. So what they did, this is the Greek letter sigma, which stands for sum. So this is the uppercase letter sigma. And what they did was they stretched it and elongated it. And that is, in fact, where the integral symbol comes from. It's an elongated Greek letter S. And it is used for the definite integral, where the definite integral is the area under the curve, which is what we're trying to find when we're looking at something like this. We're trying to find the area of this shaded region that is between the vertical line x equal a, the vertical line x equal b, above the x-axis and below the curve. So how do we use this sigma notation to simplify things? Well, when we use sigma notation, we're going to use it to write an example down here. So let me try to do a better job of drawing my sigmas today. They do have those little tick marks on them, which I am not good about drawing. And then I'm writing this larger so everybody can see it. And again, this symbol exceeds one line of notebook paper. It actually takes 3 lines. The sigma itself goes slightly over 1 line. The n equal 1 would be on the line below, and the 20 would be on the line above. And the n is actually written on the line in the center. So just like the integral symbol extends above and below the line, so does the sigma symbol. So if you were looking at line notebook paper, it would be something like this. Right? Which you should not be using line notebook paper because it is more likely that you'll make careless mistakes if you do. So switching to unlined notebook paper is the single best thing you can do to start doing better in your classes. Typically a 10% difference. So that's a whole letter grade. Now, what does it do? It stands for sum. So this represents a sum. And it represents the sum of all the numbers. If we start counting at the lower number, which is called the lower index of summation, the lower limit of summation, and we count all the way to 20, and we count by n. So first n is 1, then n is 2, then n is 3, then n is 4, then n is 5, all the way up to 20. And the sigma means each time you change the value of n, you add what you had before to the next thing. So essentially, this symbol right here represents this sum that you see right here, the sum of all the numbers from 1 up to 20. All right. So it's 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus dot, 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 plus 18 plus 19 plus 20. Right. So it's the sum of all of those numbers. Now, 20 is a not very large number of rectangles to take if you're trying to find the area under a curve, but you can tell that even that is, you would not want to have to do that by hand. I do not want to have to add these numbers together by hand. There's just no way. I can't do that. It would drive me crazy. So we use sigma notation instead, and we're going to learn something about some of the rules for sigma notation. There are some formulas. I do not expect you to memorize the formulas. I'll give them to you if you need them. And you can use the formulas to find the value of the sum of the first 20 counting numbers. Now, let's talk about notation. What is the index of summation? The index of summation is this variable right here. It's known as a dummy variable because it only shows up in the middle where you're doing the summation, and then it disappears by the end. So that would be the index of summation, also called just the index for short. So common letters to use are N, K, J, and M, as in Mary. Now, N started out as one of the most common ones, but we're going to use N for the upper limit of summation because we're going to allow the number of rectangles to get larger and larger and larger and go to infinity. So because we want to use N as a generic placeholder for the upper limit of summation, we're going to use a different index of summation. More commonly, I use K. You can use M as well, but M sounds so close to N, it's very hard to do. So M as in Mary, N as in Nancy, it's difficult. J works as well. In the past, we used to use I all the time, but now that we're doing more mathematics with the square root of a -1, the imaginary number, I has kind of fallen out of favor. So the two most common would be K and N, as in Nancy. Now, what else do we have here? We have the lower limit of summation, which is the number 1. So this is the lower limit of summation. And the 20 represents the upper limit of summation. So you start at the lower number and you proceed to the upper limit by ones. And then what is the value of the expression, or what do we call the expression that follows the symbol? This symbol right here, this part, is what's known as the summand. Remember I said we often stick AND or END onto the end of the operation to represent the thing that is being whatever. So the dividend, the thing that is being divided, and the radicand, the thing that is under the radical, and the summand, the thing that is being summed. So this is called the summand. Now, when we're looking at this, the process is, again, to start at 1 at the lower index of summation and to plug that into the expression. So in this case, we'd plug it in and we'd have 1. And then we cycle and we let N take on the value of 2. And then we add that to the previous value. So we have 1 plus 2. And then it becomes 3 plus 3. And then it becomes 4 plus 4. So each time we change the index, we add that to what was there previously. So for example, let me do, let me see where I have some space to write. Let me do an example right here. I didn't quite leave myself enough space, but hopefully you can read that. I want to do the sum from n equal 5 to 8 of n. So that means I want to start where n is 5. So I write 5. Now I want to cycle the index. So I increase the index by 1 to 6, and the symbol sigma means and add it to. So I add this, and now I let it be 6. So once it becomes 6, then I add it and let it cycle to 7. So it becomes 7, and I add that on. And then I go all the way up to the upper limit, and I stop. So I start at the lower limit, and I let n take on each of the values as it becomes the value of the index, and I stop when I reach the upper limit. So when I take these two together, this would be 11 plus 15, which gives me 26, right? And it works even if I have a different expression behind the number. So let's take on, let's see, I need to really write this a little smaller. Let's do the sum from n equal 2 to 5. of 3n plus 1. Oh, okay. What does that mean? Well, I'm going to start where n is 2, and I'm going to go to 5. So the first time that n is 2, I plug in 2 to the summand, the expression behind the sigma, and I get 3 times 2 is 6, plus 1 is 7. So my first expression when n equal 2 is 7. And then I put a plus, and now I let n be 3. And I get 3 times 3 is 9. 9 plus 1 is 10. So my next value that I'm going to add on is 10. And then I go to 4 because I'm going up to 5. So 3 times 4 is 12, plus 1 is 13. And I can see that there's a pattern developing here, that these are separated by 3. So I'm kind of expecting 16 for the next one. So when n equals 5, the upper limit of summation, I get 3 times 5, which is 15, plus 1 is 16. And then I add all of those values together, 10, 20, 30, 46, and I get 46. Right? And that's how a sigma notation works. Now, we're not going to use sigma notation terribly often in Calculus 1, but in Calculus 2, sigma notation becomes a major part of studying sequences and series, which is the most important part of Calculus 2. And it is fully 1/3 of the course. So 1/3 of the course deals with integrating products and ratios of functions, so dealing with multiplication and division in the integrand. The next third of the course deals with sequences and series and is the most important third. And the last third is sort of a hodgepodge of different things that we need to talk about, including polar coordinates and polar systems, et cetera, but sort of a combination of different ideas and topics. So now let's talk about an example. So we're going to do an example here. It says, write in sigma notation and evaluate the sum of terms 2 to the I for I between 3, 4, 5, and 6. So they're telling you that I starts at 3 and proceeds by 1 up to 6. So our lower limit of summation is going to be 3. And it looks like we're using I for the index. So we have from I equal 3, and the last value is 6. And we want to evaluate the sum of the terms of 2 to the I power. So remember, I said I used to be most commonly used. It's less commonly used now, but it used to be the most common one until we started doing so much with imaginary numbers. So now what does this mean? Well, first we let I be 3. And so we plug in 2 to the 3rd. And then the sigma symbol means add. So we add. I'm terrible at writing that sigma symbol well. So then we get 2 to the 4th plus 2 to the 5th plus 2 to the 6th. And we stop when we get to the upper limit of summation. So we start at the lower limit and go to the upper limit. So this gives us 8 plus 16 plus 32 plus 64. 64 and 16 gives me 80, and 8 and 32 gives me 40, and 40 plus 80 is 120. Right? So this is what method or notation we're going to use to help us add up the areas of all of these rectangles while we approximate the area under a curve. Now, there are some properties of sigma notation that we want to go through. And again, when we go through these properties, you'll notice that they're very similar to the properties that we talked about for the indefinite integral. If there's a constant on this one, this basically means that you have the sum. Let's say I had the sum from k equal 1 to 3 of 4. That means when k is 1, I write 4. Then k is 2, and I write 4. Then k is 3, and I add 4, which means I have 4 there 3 times. And this gives me, of course, 12, which is the same thing as taking the upper limit and multiplying by the constant that is the summand. Now, this only works if it starts at k equal 1. If it doesn't start at k equal 1, it's not quite the same. You'll get a different value. The next property is that you can take a constant and pull it outside of the summand. So for example, if we had the sum from I equal 1 to 43 of 3i squared, then I could write this as 3 times the sum from I equal 1 to 43 of I squared. So I could leave the 3 to multiply by the sum afterwards. The only thing that can't pass out of the sigma symbol is anything that depends on the index of summation. This is just like the indefinite integral. Anything that depends on the differential variable cannot pass outside of the integral. The next one is the sum and difference rule, just like we saw when we did indefinite integrals. This basically means that if we have the sum from I equal 1, and I keep using I, even though I said we use it less often now, I should change. If I have 3i minus 4, I could write this as the sum from I equal 1 to 10 of 3i minus the sum from I equal 1 to 10 of 4. So I can split it up. Now this is possible because the sigma symbol represents a sum in itself. So you have a sum of a sum. And so you can definitely split it up into the different parts. And then you could use property 2 to pull the 3 outside of the second one. The last one is a little bit more subtle and actually in some ways more important. So when I look at this last one, if I have the sum from k equal 1 to 20 of, oh, I don't know, 2i or 2k, that should be a k. It doesn't look like a k. There we go, 2k. Then this is the same as doing the sum from k equal 1 to 5 of 2k plus the sum from k equals 6 to 20. Does that make sense to everybody? In other words, if I want to go from 1 to 20, but I want to break it into parts, I could go from 1 to 5 and then from 6 to 20. And I would end up with the same thing. Now, we actually use this in order to find something like the sum from 6 to 20, because we can then subtract this sum from 1 to 5 of 2k from both sides, and we get these two starting at 1. The formulas for summations start at 1, so it's nice to have a way to solve for a sum that does not start at 1 in terms of other sums that do start at 1. Now, here are the next rules that also require us to start at 1. These are the primary simplification formulas for summations and sigma symbols. So when we're looking at these, what we have is the sum from k equal 1 to n of k. So here's an expression where the index, that dummy variable, is showing up in the summand, all right, showing up in the expression behind sigma. This means that you're going to take and let it iterate 1, 2, 3, 4, 5 until it reaches whatever n is, and you're going to add them all together. Now, there are ways to prove algebraically that this is equivalent to the product of n times n plus 1 divided by 2. So let me give you an example of what that would be. So let me put one in here. So this would be an example. Oh, and I don't know why I have the paragraph markings on. You don't need those. Okay, so we have the sum from k equal 1 to 20 of k. which is 1 plus 2 plus 3 plus 4 plus 5, all the way up to 19 plus 20. All right, so it's the sum of the first 20 numbers. Now, yeah, it's 20 numbers and they're all pretty simple, but I really don't want to sit here and add all those 20 numbers together. So there's a formula to do it, and the formula says take the upper limit of summation and multiply it by itself plus 1. So 20 times 21 and then divide by 2. That's 210. That's much faster than adding those 20 numbers together. This does require that the summation starts at 1. All right? Must start at 1. So what are you going to do, for example, if instead of starting at 1, you have something that starts at, oh, I don't know, let's pretend. What if instead you have the sum from k equal 4 to 62? All right. What are you going to do if you have the sum from 4 to 62 of k? Well, first you're going to say this is equal to the sum from k equal 1 to 62 of k minus the sum from k equal 1 to 3, right? You want to start at 4. So you have to get rid of the first 3. So you're going to say that's the sum from 1 to 62 minus the sum from 1 to 3. And then you can apply the formula to each one of these in turn. So you get 62 times 63 divided by 2 minus 3 times 4 divided by 2, which is going to give me 31 times 63, which is 33,453 minus 6, which is 33,447. So that's how we use that previous rule that we saw where we can rewrite it in terms of other ones. So we write it as the sum from 1 to 62 minus the sum from 1 to 3, where 3 stops just short of where I wanted it to start. And so then this will just give me the sum from 4 to 62. Okay? All right. Let's take a look at the next example, which is the sum of consecutive integers squared. So this is a little bit different. It must start at 1, just like the previous one. And this time, what it has instead is it's got the square of k behind the summand. And this is a slightly different formula. So we're going to have a different formula here. Let's say that we want to do the sum from k equal 1 to just 6 of k squared. Now, I could write this out. This is 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared. That one's short enough. I could write it by hand if I wanted to. All right. But to square them and add them together is kind of a pain because there's a lot of numbers there, and the numbers are going to get larger as I square them. So the formula says take the upper limit of summation, which is 6, multiply it by 1 more, which is 7, then take the upper limit of summation 6, double it, 12, and add 1, 13, and divide that by 6. Now the proofs of these take a fair amount of time, and it's not something that's so important that we want to spend the time on it. It comes up in probability and statistics most often. So if you want to see it, you can Google it. I don't believe it's even in your textbook. And this gives us 7 times 13, which is 91, because the 6's cancel, of course. All right, now that's not normal. They're not usually going to be something that cancels, but that's what you have. All right. Again, if it does not start at 1, then you're going to have to do this subtraction trick to get it started at 1. So if you had the sum from k equal 10 to 32 of k squared, you would do the sum from k equal 1 to 32 of k squared minus the sum from k equal 1 to 9 of k squared. Take off the ones that you didn't want, all right? And then in order to simplify this, you multiply by 32 times 33. Double 32 is 64 plus 1 is 65, all divided by 6 minus, and then this is going to be 9 times 10 times 19. Double 9 is 18 plus 1 is 19 divided by 6. So let's see, 6 and 33 are divisible by 3. That leaves a 2. 2 goes into 32 and leaves 16. So I have 16 times 11 times 65, which is 11,440. And then 3 and 9 are both divisible by 3, and then 2 goes into 10, which leaves 5. So 15 times 19, which is 285. And you get 11,155. Now, there's no way that I could have done that by hand in anywhere near that amount of time. So summation is a good way of doing a lot of summation, a lot of adding of many numbers more rapidly and more easily. There's also a formula for the cube. The cube does not come up as often for us, so you won't see this one as often. We'll see the square and we'll certainly see k quite a bit, but we won't see the cube as often. But the formula is n squared times n plus 1 quantity squared divided by 4. So let's do one really simple one. Oh, let's see. Let's do the sum from k equal 1 to 15 of k cubed. Oh, let's make it 3k cubed. Remember, you can pull the 3 to the front. K equal 1 to 15 of k cubed, which is going to be 3 times, and now you do the formula for k cubed, which is going to start with n, which is 15. This one again must start at 1. And so we have 15 squared times 15 plus 1 squared, so that's 16 squared over 4, which is, well, 3 times 225 times 256 divided by 4, whatever that comes out to be. It's still going to be a fraction, I believe. No, it's not. The 4 is going to cancel completely. Okay, so 3 times 225 times 256 divided by 4. I got 43,200. Can I get verification? Did anyone else get that amount?
Yep.
All right, yay. Okay, so now let's just practice a couple of these. We want to write sigma notation and evaluate the sum for the following expression, 4 plus 3k for k going from 1 to 100. So sigma notation, who wants to tell me what the lower limit and upper limit of summation should be? This should be k equal what to what?
1 to 100.
Yep. And someone else tell me what the sum end is.
Four plus 3k.
4 plus 3k. Okay. Now the first thing that we see is we've got this summation right there, which means we can split it into the sum of each individual term. So we can split this into k equal 1 to 100 of 4 plus the sum from k equal 1 to 100 of 3k. Now, is there another way that we could split up one or both of these terms?
But wouldn't it be, are we also adding in the 4? Like, isn't
The 4
4 like a
is part of
constant?
the summand. So it's being added 100 times. So it's included in what's being added 100 times. So for example, if you're wondering what this would look like, first k would equal 1, and you would write 4 plus 3 times 1 plus, then k would equal 2, and you would write 4 plus 3 times 2, and then k would equal 3, and you would write 4 plus 3 times 3, and then k would equal 4, and you would write 4 plus 3 times 4. Does everybody see what you're writing? How the summation works now? I think you're getting a little confused on what would be done. If you started at this one, this is what you would have written up. Now, if you split it up, notice that the 3 is a constant being multiplied by k, so we can take that part out. So we could rewrite this one as the sum from k equal 1 to 100 of 4 plus the sum from k equal 1 to 100 with 3 out front and k behind. Now there's a rule for 100, the sum of k equal 1 to 100 of a constant. Let's see what it is again. So that's one of the properties. So I'm going to click up here. So the property is, if you're going from 1 to n of a constant, multiply the upper limit of summation by the constant. Now this requires that you start at 1, all right? This must start at 1. So we're going to come down here to example 2, and we're going to start with 100 times 4. All right, that's our first rule. Okay, what about the sum of 3 times? So this is going to be 3 times something. The sum from k equal 1 to 100 of k, isn't that a property as well? That's one of these properties, the rule, which is the sum from k equal 1 to n of k is n plus 1 over 2. So the upper limit is 100, and then 100 plus 1, and then divided by 2, which gives us 400 plus, what does that come out to be? 3 times 50.
I got 5,050.
And then times 3.
Yeah, and then I get I don't remember what, because I added 400.
15,150. Your answer was correct. And then this would give us, plus the 400, would give us 15,550. Right? Are there any questions? Okay, let's try another one. This is the sum from k equal 1 to 20 of 2k plus 1. And again, just to remind you, if you were actually to multiply this out, you would let k equal 1, and you would have 2 times 1 plus 1, plus, now k equals 2, 2 times 2 plus 1, plus, now k equal 3, 2 times 3 plus 1, plus, now k equal 4, 2 times 4 plus 1, plus, plus, and it goes up to 20. So k equal 19, 2 times 19 plus 1, plus, and k equal 20, 2 times 20 plus 1. But that would mean you would have to do all of the arithmetic by hand, which is super onerous. So we don't want to do that. So take a moment, split it up, apply the formulas. And then we'll compare answers. Once you get your answer, put your answer into the chat window and we'll compare answers. Oh, yay. Everyone's coming up with 440. Yes. Right? So we got it. Okay. Great job. Now let's look at one where it's not starting at 1. So this one is going to be a little bit different. And in this one, we've got the sum from k equal 5 to 10 of k. So we've got the sum from k equal 5 to 10 of k. We cannot do the formula yet because it doesn't start at 1. So we're going to write this as the sum from k equal 1 to 10 of k minus the sum. Where should I start the next one to get rid of the first ones? Start it again at
1 and then
1
go to 4.
and go to 4. And now I can apply the formula. So when you get your answer, throw that into the chat window and we can compare. So I've got 10 times 11 divided by 2 minus 4 times 5 divided by 2, which is 55 minus 10. Excellent. 45. Okay. One more example. This is a longer one and it has a k squared. So let me go up to the rule and I'll copy off the rule for k squared so that you can see it in the same place. Uh-oh. I weirded out my word. Now it's not responding. I knew better than to do that. Come on, word. Come back to me. All right, you guys work on it while mine's okay. It did manage to come back. Okay, here's the formula, right? So I'm going to stretch it out as much as I can. Notice that the 100 does distribute over the entire thing. So you can either keep it on the outside or you can pull it in or whichever way you prefer. When you get your answer, go ahead and throw it in the chat window. Excellent. Looks like everyone is coming up with the right solution. So it looks like you're masters of summation notation, which will be really helpful when you get into calculus 2. We're talking about sequences and series. This is the backbone of series. So this notation, so it's not going away. Now what we want to look at is we want to look at approximating areas. So we're switching now to do something slightly different. Now that we have the notation down, we're going to look at approximating areas under a curve, between a curve and the x-axis.